Space. It's vast and beautiful, full of stars and planets, but space can also be dangerous. It holds giant rocks called asteroids. These asteroids hurtle through space at incredible speeds. Most asteroids are far away, but some come close to Earth. These space rocks vary in size. Some are as small as cars, while others are bigger than cities. It's the big ones we need to worry about. If a large asteroid hit Earth, it would be catastrophic. The good news is that scientists are always watching for these threats. They use powerful telescopes to track asteroids and predict their paths, and they are developing ways to protect our planet from a potential impact. Earth has a history of asteroid impacts. The dinosaurs were wiped out by a massive asteroid millions of years ago. That impact caused widespread destruction and changed life on Earth forever. Even smaller asteroids can cause significant damage. In 2013, a meteor exploded over Chelyabinsk, Russia. The explosion was equivalent to a small nuclear bomb and injured over 1,000 people. These events remind us that the threat from asteroids is real. While the chances of a major impact are low, the consequences would be severe. That's why scientists and engineers are working hard to develop planetary defense systems. Our future may depend on our ability to deflect or destroy asteroids before they reach Earth. The survival of our species could hinge on our preparedness for this cosmic threat. For decades, the idea of using nuclear weapons to defend Earth from asteroids has lingered in the minds of scientists and filmmakers alike. It seems counterintuitive, almost reckless, to fight one destructive force with another. Yet the sheer power of a nuclear blast might be the key to diverting a planet-killing asteroid. This isn't about blowing up asteroids Hollywood style. That would be messy and potentially make things worse. Instead, scientists envision a more controlled approach. Detonating a nuclear device at a calculated distance from an asteroid could vaporize part of its surface. This vaporization wouldn't destroy the asteroid, but it would act like a giant rocket engine, pushing the space rock off its trajectory and away from Earth. Think of it as giving the asteroid a gentle nudge, albeit a very powerful one. The concept hinges on a fundamental principle of physics. For every action, there is an equal and opposite reaction. When the nuclear blast vaporizes part of the asteroid's surface, it creates a massive plume of gas expanding outwards at high speed. This expulsion of gas acts like a rocket engine's thrust, pushing the asteroid in the opposite direction. The larger the asteroid, the more powerful the blast needed to create a sufficient push. But the principle remains the same. It's a delicate operation, requiring precise calculations and timing. Detonate the nuke too far away, and the asteroid might only feel a slight nudge. Too close, and you risk shattering the asteroid into smaller but still dangerous pieces. A controlled chaos. To investigate this potentially planet-saving technique, scientists at Sandia National Laboratories in the United States have been conducting experiments. They're not detonating actual nuclear weapons, of course, but they are simulating the extreme conditions of a nuclear blast. Using powerful lasers and X-ray pulses, they're replicating the intense heat and radiation a nuclear explosion would generate in space. These simulated blasts are directed at small-scale models of asteroids made from various materials, allowing researchers to study the effects up close. These experiments are providing invaluable data on how different types of asteroids might react to a nuclear detonation. The findings will help refine the calculations and improve the accuracy of any future planetary defense system that might rely on this powerful yet potentially hazardous technology. Recreating cosmic chaos. Imagine trying to recreate the power of a nuclear blast, not in some desolate wasteland, but within the confines of a laboratory. That's the challenge the scientists at Sandia National Laboratories embraced. Their mission, to understand precisely how a nuclear detonation could deflect an incoming asteroid. Instead of actual nuclear weapons, which would be impractical and wildly unsafe for a laboratory setting, the researchers turned to sophisticated substitutes. Powerful lasers and X-ray generators became their tools of choice, capable of producing short, incredibly intense bursts of energy. These bursts, lasting mere fractions of a second, mimic the thermal radiation unleashed by a nuclear explosion. Directed at small-scale asteroid models, these artificial blasts allow scientists to study the effects of vaporization in exquisite detail without the need for a catastrophic detonation. A glimpse into the maelstrom. These experiments are not just about brute force. They're a delicate dance between energy and matter. The scientists use high-speed cameras capable of capturing millions of frames per second to record the fleeting moments of the blast. These recordings reveal a ballet of destruction and deflection. The simulated nuclear blast instantly vaporizes the surface layer of the asteroid model, creating a superheated plume of gas that expands outward with incredible force. This is the crucial moment where the destructive power of the blast translates into the saving grace of deflection. The expanding plume, following Newton's third law, imparts an equal and opposite force on the asteroid model, pushing it away from the simulated path of Earth. One might wonder, wouldn't the asteroid, even if partially vaporized, simply continue on its trajectory due to its immense mass and momentum? The answer lies in the surprising power of the vaporization process. The rapid expansion of the vaporized material, reaching temperatures of tens of thousands of degrees, creates a significant thrust. While the asteroid itself may be massive, the momentum transfer from the high-velocity plume is enough to alter its course. Think of it like a rocket launch. The rocket itself is heavy, but the high-speed expulsion of gases from its engines generates enough thrust to overcome gravity and propel it upwards. Similarly, the vaporized asteroid material acts as a temporary rocket engine, nudging it onto a new path. The Sandia experiments are not just about proving a concept, they're about pushing the boundaries of what's possible. The researchers are testing different asteroid compositions, varying the energy levels of the simulated blasts, and analyzing the resulting deflections with incredible precision. Their findings suggest that this method could be effective in deflecting asteroids up to a certain size, potentially those several hundred meters in diameter. However, larger asteroids, those measuring kilometers across, would likely require multiple blasts or a different strategy altogether. The Sandia experiments represent a crucial step forward in understanding and developing viable planetary defense systems. They demonstrate that even in the face of a cosmic threat, human ingenuity and scientific rigor offer hope for safeguarding our planet. While the idea of nuking an asteroid might grab headlines, it's not the only strategy scientists are exploring. There's a whole toolbox of potential deflection methods, each with its own strengths and weaknesses. One promising approach is the kinetic impactor, a spacecraft designed to slam into an asteroid at high speed. The impact transfers momentum, slightly altering the asteroid's trajectory. Sounds simple, but timing is everything. A small nudge years in advance can make all the difference. Then there's the gravity tractor, a spacecraft that uses its own gravitational pull to gently tug an asteroid off course. It's like a cosmic game of tug-of-war, requiring patience and precision. This method works best on smaller asteroids and requires years, if not decades, of lead time. Other more futuristic ideas include using focused solar energy to vaporize asteroid material or deploying swarms of small reflective spacecraft to alter an asteroid's path by reflecting sunlight. Each method has its proponents and its challenges, making planetary defense a vibrant field of research. A tale of two defenses, nukes versus kinetic impactors. So, how does the nuclear option stack up against these alternatives? Let's compare it to the kinetic impactor, a method already tested in space. In terms of sheer power, nuclear blasts win hands down. They can deflect larger asteroids and potentially offer a solution when time is short. However, nukes come with political and ethical baggage. There's always the risk of unintended consequences, such as fragmentation of the asteroid or radioactive fallout. Kinetic impactors, while less powerful, are a more controlled and internationally palatable option. NASA's DART mission, which successfully altered the trajectory of a small asteroid moonlet, demonstrated the viability of this approach. However, kinetic impactors require years of advance warning to be effective. The choice between a nuclear blast and a kinetic impactor isn't just about physics, it's about weighing risks, benefits, and international cooperation. The ideal scenario might involve a combination of methods tailored to the specific threat we face. The need for speed when time dictates strategy. In the cosmic game of asteroid deflection, time is often the most critical factor. The further in advance we detect a potential impact, the more options we have. But what happens when a large asteroid appears out of nowhere on a collision course with the Earth and we only have a few years or even months to react? This is where the nuclear option might be the only viable solution. While kinetic impactors require years to alter an asteroid's trajectory significantly, a well-placed nuclear blast could provide a more immediate course correction. Of course, such a scenario would require careful international coordination and a calculated assessment of risks. The decision to use nuclear weapons in space would not be taken lightly, but the survival of our species might depend on it. The threat of asteroids is a stark reminder of our vulnerability in the cosmos, but it's also a catalyst for scientific innovation and international cooperation. By developing a range of deflection methods and enhancing our early detection capabilities, we can increase our chances of avoiding a cosmic catastrophe. Weighing the nuclear option. The prospect of using nuclear weapons to deflect asteroids sparks debate. Experts in planetary defense provide balanced perspectives. Professor Colin Snodgrass emphasizes understanding lab findings in real-world scenarios. Scaling results to full-size asteroids is crucial. The HERA mission will survey DART's impact aftermath. Professor Gareth Collins prefers non-nuclear methods but acknowledges nuclear potential. Kinetic impactors offer a controlled approach. For large asteroids or limited warning, nuclear might be our only recourse. Expert opinions highlight the complexity. Nuclear blasts offer power but come with risks and ethical considerations. Non-nuclear methods may not always be sufficient, especially when time is critical. Scaling up the science, from lab to cosmos, bridging the gap between laboratory experiments and deflecting an actual asteroid hurtling through space is a monumental challenge. The Sandia experiments provide a crucial foundation, but real-world asteroid deflection involves a whole other level of complexity. For starters, asteroids are not uniform spheres like the models used in experiments. They come in various shapes, sizes, compositions, and rotation rates. A successful deflection strategy must account for these variables, which can significantly influence the outcome of a nuclear blast. Moreover, the space environment itself is a dynamic and often unpredictable place. Solar radiation pressure, gravitational influences from other celestial bodies, and even the outgassing of the asteroid itself can affect its trajectory. Overcoming these challenges requires sophisticated modeling, advanced spacecraft technology, and precise navigation capabilities. It also necessitates international collaboration, as asteroid threats are a global concern, requiring a unified response. A multifaceted shield blending strategies for planetary defense. Given the diversity of asteroid threats, a single deflection method won't suffice. A multifaceted system offers the most comprehensive protection. Early detection is paramount. The sooner we identify a potential impactor, the more time we have to react. Continuous monitoring using ground-based and space-based telescopes is essential. Characterizing its size, composition, and trajectory is crucial. This helps determine the most effective deflection method. For smaller asteroids, a kinetic impactor or gravity tractor might suffice. For larger asteroids, a nuclear option might be necessary. By pooling our knowledge and resources, we can safeguard our planet for generations to come. The nuclear dilemma, a double-edged sword of salvation. Using nuclear weapons to protect our planet presents a profound dilemma. A force capable of unimaginable destruction, a stark reminder of humanity's capacity for self-annihilation. Yet this force might safeguard us from a cosmic threat. Sandia National Laboratories explores nuclear asteroid deflection. Vaporizing an asteroid's surface can alter its trajectory. Deploying nuclear weapons in space poses ethical and political challenges. It requires unprecedented international cooperation. Guardians of the pale blue dot. As we venture into space, we must remain vigilant about potential threats in the cosmic expanse. Asteroids remind us of our planet's vulnerability. Protecting Earth from impacts is a shared responsibility. It requires global collaboration. We have the tools and knowledge to address this challenge. From kinetic impactors to gravity tractors, we are forging a planetary shield. The future of humanity depends on our ability to deflect these celestial wanderers. It's a challenge that calls upon our ingenuity and collaborative spirit.